So we are starting a new section. It's about aliasing and frequency warping. Okay, so where are we pitching this? Now, there are so many things that you study here, right? Sometimes you might get lost. Where are we right now? Okay, how these things are fitted together. Certain things are actually generally applicable, and certain things are applicable in association with the other elements, right? So therefore, it is very important that you understand that these pieces are fitted together in this format. Okay. So in that context, where are we pitching this aliasing and frequency warping? So let me tell you this in a generic form, right? Um, so we are dealing with signals, okay, and signals go in a loop, and we convert the signals from continuous to discrete, taking samples and all. When we do that, or in generally in signal processing or discrete signal processing, right, we might lose information. That is a general problem. Okay, so you can study this as an abstract problem, right, which is generally applicable to control systems or any signal processing entity. Okay, right. So to add to that, let's say I have a certain frequency information. I have 10 hertz, I have 20 hertz, I have 50 hertz signal. Okay, so that is basically the entire information. Then I process the signal, right? Whatever frequencies, 10, 15, 20 maybe, right? Do some sort of analog to digital conversion and other things. Different equations are there in discrete controls, right? And you calculate you integrate signals, you differentiate signals using their samples. You do a lot of things on the discrete domain. And at some point, you have some information. And originally it was 10, 15, and 20 hertz. Now, if you look at what sort of frequencies you have right now, if you get exactly 10, 15, and 20 hertz, which means irrespective of the processes that have been going on in the process up to now, the frequency information is not affected. The information is intact. Okay, this is the best scenario. This is the best scenario. But unfortunately, it's far from reality. So whenever you do this discrete signal processing, right? Um, for example, when you want to calculate the rate of change of a signal, you take two samples and get the difference divided by time. And if you want to implement, say, a discrete PID controller, you need to get the integral of the error. So how do you do that? You have samples, previous error, now, and like that. So combine these samples together and approximate the error integral. So when you do that, you're losing your frequency information. So is that clear to everybody? So this is the problem. We are going to analyze this and how it affects, and also to look at how we can get rid of this problem, because in a control system, if frequency is going to change, right, it might have an adverse effect on the system performance. And also there's what is called frequency warping. If you can see it on screen, right? What is warping? Warping means one frequency changes to another one in a highly nonlinear manner. Okay. So, uh, so if you look at what you have finally versus what it was initially, right? There's a difference. So is this difference okay? Or if it is not okay, what are we going to do about it? So therefore, this is going to be very abstract content that we learn. So I think you will find it very interesting. So to explain you this further, let me take a little example. Right. So what is the example over here? Um, so I put this equation first to recap your memory. Omega equals 2 pi f. You know that. This is the radian frequency, radians per second, and the F is the cyclic frequency, how many cycles per second. Okay, and also this is WD, and FD means damped in control systems. This is what we see as frequency. If you connect an oscilloscope to a plant and you see the response, it's sinusoidal, and that is the damped frequency of the plant. Okay, damped after undergoing this damping and all that. Just past information, you are familiar with that. So let's say we have a plant with the damped frequency of 4 radians per second. 4 radians per second, right? So if you put 4 radians per second over here, right, you will see uh, uh, you can convert the frequency and then to sampling interval, right? Because 1 over frequency is the interval. So when we say 10 hertz sampler, which is 1 over 10 a second sampling, you know that, right? So um, let's say we sample this waveform at 1 hertz. So one sample every second. So what's going to happen? So this is very basic signal processing. You are taking samples of a continuous signal. Okay, very basic. So even with that, you will understand there's something seriously wrong about how we do, right? So sampling is like 1 hertz. Sampling is like 1 hertz, right? So every 1 second, you take a sample. Now, if you look at what what is being sampled, it is 4 radians per second, 4 radians per second waveform. So if you put 4 radians per second here and calculate your frequency of the damped response over here, right? You can calculate FD. This is 4, this is 2 pi, right? So FD is equal to omega D over 2 pi. All right. So omega D equals 4. And if you put 4 over here, FD is 0.64 hertz. So you have 0.64 hertz waveform, and you are sampling this at 1 hertz. Can somebody tell me, is this right or wrong? Can you sample a waveform accurately, right? If your sampling rate is not about twice the signal frequency. No. I think you have learned this. You may have forgotten it. You cannot properly sample a frequency unless you sample it at least twice of the signal frequency. Now, the signal frequency here is 0.64, right? If you take twice of that, it will go above 1, right? 1.28 to be exact hertz, and you're sampling at 1 hertz. This is under sampling. You are breaking fundamental law of Nyquist. So this is not proper. We know that. Now we come back to the board here and see what's happened. Right? This is a rotating phasor kind of thing, right? And over here is the first sample. Let's say you take the first sample of the waveform over here, and then you take the second sample after 1 second. So after 1 second means the signal, the sinusoidal waveform, let's say it's a sinusoidal, it goes like that. And over here, after 1 second, you take the second sample because you take the samples after 1 second. Okay. So so what's going to happen here? First sample, second sample. So you have come over here more than 180 degrees in phase when you are taking the second sample. So if you are if you collect the samples like that, right, and produce it to someone else, and he doesn't know that you have violated this fundamental law, Nike's law. He just look at your samples and he thinks that you have gone not this way but that way. You can go to the same point in two directions, right? Anti-clockwise or clockwise. Usually we go anti-clockwise, positive direction. And everybody thinks when you produce a set of samples, these samples are taken anti-clockwise, positive sense. But here it is not the case. You are taking samples in the opposite direction. Okay, right. So if I write down this equation over here, right, the total angle from here to here, right, is frequency times time. Okay, so omega d times t. T is the sampling interval. So omega over here, omega d over times t. This is the total angle from here to here. And we subtract this angle from 2 pi, right? Then you get the positive angle, this angle. And I give it a name, WAT, or omega 80 rather. So there are two processes, right? Counterclockwise process and the clockwise process. Counterclockwise process, right, is faster because it goes a long angle in 1 second. The clockwise one, which is fictitious, and it is slower. Okay, therefore it goes a small angle, right, during the same capital T time. So is that clear to everybody? This equation up here. Omega 80, omega A was not there in the plot, okay? The signal was omega D. This is the genuine signal. And omega A is not a signal that was there or that is there in the plot. It is a fictitious thing, created waveform. And it is negative frequency also. So then we divide every term in the equation by capital T, and you get it like that. And 2 pi over capital T is sampling frequency. You know that, right? And omega D is the signal frequency. Omega A is what is called alias frequency. Something new, something you artificially create, something the sampler creates its own. Okay. And when you convert this into cyclic frequency, F, by multiplying by 2 pi or divide by 2 pi every term, you get FA equals Fs minus FD. So FD is the damped frequency, FA is the sampling frequency, FA is the aliasing frequency. This equation holds whenever you break the Nyquist theorem. Whenever you sample a signal less than twice of the signal frequency, you can use this equation to calculate what it looks like after sampling. What it looks like after sampling, okay? And we have a numerical example here. And if you work it out like that, right, 4 hertz, 4 radians per second signal sampled at 1 hertz, what's going to happen, right? So this is the result. Omega D is 4, omega S is 2 pi, because 1 hertz is 2 pi in radians, okay? Every 1 second, it takes 2 pi. So omega A, this equation is equal to omega S minus omega D. And in cyclic frequency, it is Fs minus Fd, 1 minus 4 over 2 pi. That is negative 0.36 hertz. Is a negative frequency. Now, if you look at this one, right, 0.64 hertz signal, right, now looks like minus 0.36 hertz signal. It's one-way negative. On the other hand, it's also a lower frequency. A lower negative frequency is created, which is completely absurd. There was no such thing in the plant. And when you do the sampling, you are not supposed to generate this kind of signals. Okay. You are supposed to sample the same frequency, but samples. But now, if you look at the samples, you cannot reconstruct the original waveform. It's complete nonsense. And we call it alias. So you have to be very careful when you select samplers. Make sure your sample is at least twice as fast as your bandwidth frequency. Bandwidth frequency means the maximum frequency that you deal with, and your sampler should be few times of that frequency. Remember, just before the break, we discussed about observer-based control. There, the observer improves the bandwidth. So you originally decide a certain bandwidth. Now it's little more than that. And you allow higher frequencies to come in. And there's a sampler which takes the samples properly before the observer. Now with the observer, it fails because now it generates aliases. Okay, because the sample is now not fast enough, not as twice as fast as the bandwidth frequency, because bandwidth has been increased, okay, with the observer-based design. Now see, this is how things interact each other in the control design process. So this alias signal, which is low frequency and negative frequency that is generated by the sampler purely because of slow sampling, is called alias, and it's a ghost signal, right? You know what I mean. Any questions about aliasing? All right. Now, so let's read through this. Sampling at the rate of fs maps all the frequencies into the unit circle, right? And over here you can see the unit circle, very famous in discrete controls. Everybody knows that as long as you are mapping into the unit circle, you are stable. Okay. So now this is your continuous time domain, right? S-plane, right? And what is this pi over t? This is the frequency axis, and this is the Nyquist frequency. Nyquist frequency, right? So half of the signal frequency, right? Pi over t. So here you can see it, omega equals 2 pi f, right? And if you look at the sampling frequency fs, this is the sampling frequency in radians per second. This is the radians per second axis. And then you replace fs with 1 over ts, right? Like that. And half of the sampling frequency, this is the sampling frequency, half of that is pi over ts, right? This is the maximum frequency that you can sample properly, coming from the sampler side. Okay. So if your sample is 10 hertz, you can sample a signal up to 5 hertz, something like that. So in the frequency axis, it is pi over sampling interval. Pi over sampling interval. So you calculate it based on your sampler and draw a line, positive and negative axis. And anything in this area, right, plus or minus pi over t, are properly sampled by the sampler. Now you have a sampler, and once you draw this one, you can tell any frequency within these margins, boundaries, have no problems, right? They're properly sampled. and they are mapped onto this one. What about the other frequencies above this and below this? Can somebody tell me anything about it? So you have a 20 hertz sampler. It can sample all the frequencies up to 10 hertz. There's no problem with that. And let's say you have a 30 hertz waveform and you know it's not properly sampled. What happens? If you look at this equation, you can figure out that the higher frequency that are not properly sampled will generate a ghost signal, which is low frequency and negative. So therefore, other frequencies higher than pi over t will also be mapped onto the unit circle because they're low frequency. Understand? You will never go out of the unit circle, but this is an erroneous mapping. This is not correct, but they are mapped onto the unit circle, right? So therefore, you don't see an apparent or imminent problem here, but your signals are deteriorated. There are ghost signals going through your loop, and you don't get what you expect to get, right? The response is different, but it looks everything is okay. But there's a certain problem, aliasing. So remember that. So just because you have everything within the unit circle doesn't mean that everything is okay, right? Particularly the sampler. If it is undersampling something, right, you can get higher frequencies aliased into lower frequencies and well within the unit circle, and you might not notice it. Now, the next question is then how to avoid aliasing. Can I have some of your answers? Can anybody propose something? How to avoid aliasing? Can you guys unmute your mics and answer the question? Any suggestions? How we can get rid of aliasing?
Filter out higher frequencies that are not applied to the Nyquist criteria.
Right. So if you know your sampler is 30 hertz, what do? You have a 30 hertz sampler. So what do you do then?
Filter out all the frequencies higher than 15 hertz.
Yes, correct. Do not let anything above 15 hertz or even further is better. Even 5, 6 hertz is much better, so that you don't have this problem, right? Yeah, correct. That is one answer. You may have heard this in somewhere, right? Multiple places. High-speed sampling. The first thing is you check the system bandwidth, right? Because system bandwidth is what you want. You are not actually designing starting with a sampler. Even though we just explained about the sampler, you don't bring a sampler down and design the control system around it. No, you design your sampler according to what you want. Okay, your bandwidth, your phase margin, etc. You decide what you want there and purchase the sampler that is appropriate. That is what you do. Okay, so the first one is high speed sampling, twice as fast as the highest signal frequency. This is the generic way. Now, the second part is, of course, as you pointed out, anti-aliasing filtering. For some reason, there's a sampler. Now, you want to go ahead and design the system, then of course, the only option remaining to you is anti-aliasing filtering. So you have the sampler here, and in front of that you put anti-aliasing filter. So which is half of the sampling frequency over here, right? So omega less than pi over t. Then you are okay. You don't allow any signal that is above half of the sampling rate to go into the sampler to create aliases. Correct. Now let's say you have got aliasing properly done, so there's no aliasing, everything is right. Maybe that problem is not there anymore, but there are other problems. Signal warping, right? Because sampling is just one digital signal process, but there are other digital signal processes. When you implement a discrete controller, differentiation, integration, they're all happening using samples, and there also you get anomalies. So now we are going to look at that part. We don't call it aliasing because it's different. We call it signal warping. Signal warping, right? It's like warping. You know what warping is, right? You have a certain plane, flat, and all, right? So then all of a sudden you warp the surface, right? Some sort of nonlinear um, change is happening within the process. So to explain that to you, I want to first take your attention to these two things: forward difference method. So starting from Euler, Newton, every mathematician, right, they have used these difference equations, approximate versions of the continuous different signal aspects in continuous time. One thing is very famous is forward difference. What is forward difference? Forward difference is the signal at k plus 1 minus the signal at k. You see the difference divided by time, right? So let's put it as an error if you want, right? So then if you rearrange this one into k minus 1, one step behind, right? Change this case to k minus 1. So this becomes just k, this becomes k minus 1 divided by time, right? This is a forward difference method for 2 time steps, right? So out of that, you want to get ik. So you are operating here, let's say, an integral controller. You want to calculate what is the error integral up to now, right? So ik is equal to ik minus 1, right, plus ek minus 1 times time, right? Now it comes very clear to you. This is the numerical integration. Okay, this is numerical integration. Say error integration, right? So you have some accumulated error at k minus 1. Now you want to calculate the accumulated error at k. So what you do is you are adding error at k minus 1 multiplied by time t. So this is the additional error times time, right? Additional area under the error curve that you add to ik minus 1 to calculate ik. So you have been using this, right, for years now, right? It is one of the methods that we use to implement numerical integration in discrete time, okay? There's another way to do that. That is what's called backward difference method. This is forward, this is backward. So what is that? In backward difference, there's fundamental difference here, right? We write backward difference as ik minus 1, right? This is forward. Ik plus 1 means like future time minus present time. Here, the present time minus past time. Okay, so whether you are working with future and now, or now and the past, that is the difference between forward difference and backward. So if you look at the backward difference, again you can find out ik, right, is equal to ik minus 1 plus ek times t. Now see these two uh, uh, these two equations, this one and this one. Right? We have been using these equations, right, for numerical integration. They're both uh, ik on the left hand side and ik minus 1 on the right hand side, plus this quantity is the only difference. Is it ik minus 1, the previous error times time, or ik present error times time? Which one is better, right? So let's say we have this situation. There's a PID controller and there's an error coming into the PID controller, and you have to implement the PID over here, KP, KD, and KI. And of course, you have to do this in the discrete domain now. So some sort of approximations are required for error rate, and error integral, right? But to demonstrate you the point, we will take only the integration part here, right? And see what's going to happen here. So to implement this one, we need S and 1 over S. S for differentiation, 1 over S for integration. Okay, so derivative and integration. Let's take the forward difference equation, right? Forward difference equation, this one first, which says the error integral is the previous error integral plus previous error times t. So if you draw it over here on the timeline, this is time k minus 1 k, right? And there's some accumulated error at this point, which is I k minus 1. This f stands for the forward difference, right? K minus 1 is the time over here. There's some integral of the error at that point, and to which you add ek minus 1, error at that point times time. Okay, so a rectangular piece is added. And this is the actual signal. It ends up over here. And obviously, you see there's a little area here that you have not added. You have missed that area. So therefore, there's a certain error here. Your integral is not perfect. Okay, right. So now knowing that, on a different line, we will proceed the equations here, right? So what we do is we convert this into Z domain, discrete domain. So IFK becomes IFZ, right? So IFK minus 1 is the previous sample. So if you convert it into Z domain, it will be IFZ. In front of that, Z to the minus 1. All right. Plus this one, Z to the minus 1 EZ, error, because of the time difference, Z to the minus 1 comes in front of that. So using the Z transformation, right, very easy case here, just time delay, right? Please make sure you have some practice and you have no allergy to this kind of transformation, and you are familiar with that one, because it will help you to transform from time to Z world. Okay. And after that, what we do is we can see IF Z here and here. Take this one to the left hand side. So it will be Z minus 1 IF Z. By the way, you multiply every term here, each term here with Z, so that there's a Z here, and these minus ones cancel out. Okay. On the right hand side, you will retain with t times Ez, t times Ez. And after that, you isolate IFZ on the left hand side and takes Z to the Z minus 1 to the right hand side. You get this equation. So what is this equation? On the left hand side, the integral of the error. On the right hand side, the error. So this is the integrator, therefore. So very much like this. You have error going into a block, and what comes out of the block is error integral. So this is the integrator then. Okay. It's summing up error times time, error times time, error times time, and update the integral. So when you have this equation in this format, you will see error as the input, and t over z minus 1 is the integrator, which will explain you what's happening in the forward difference numerical integration. And what it produces is integral, error integral. So therefore, we can say in the time domain, the integrator is 1 over s. In the forward difference method, this 1 over s is approximated by t over z minus 1. T over z minus 1. Is that clear to everybody? Any questions, please? All right. Now, if you look at this signal conversion, S is approximately equal to Z minus 1 over T. You flip the sides to get 1 over S to S on the left-hand side. And this is the approximate expression in the Z domain. And if you want to get Z out of that, it is 1 plus TS on the right-hand side. So if you use the forward difference integration, this is the relationship between Z and S. Now, what we want to do is we want to see the mapping from S to Z, right? So this is our S plane. And on the left-hand side is the stable region. The entire negative real axis, this area is stable. So all of these points, we want to find out where we are going to map these points. Well, if you take one of the points here, say origin, right, s equals 0. So in this equation, when s is 0, z is 1, z is 1. So this point is mapped onto this point. Okay, so no problems. And if you look at another one, farther away, the negative infinity, right? If you put that one over here, z will also be negative infinity, right? So this point 2 maps to visually similar point over here. So therefore, we can say the entire negative half plane is mapped onto the entire negative half plane here as well in this mapping, right? This is how you find out a mathematical relationship and visualize what's going on, right? When you do the signal conversion using a forward integration method for integration, right? Numerical integration. So you will see there's big unstable area here because anything out of the unit circle is unstable, right? Whereas this entire negative half plane is stable. So you can actually map a stable point into unstable point over here. This method. Therefore, it is potentially risky to use forward difference integration. Right? You may have done this for many applications, but without knowing this kind of mapping, is potentially risky because the integrator will integrate and gives you something which is not very correct, and you are acting on that. Okay, so you see the proof here, mathematical proof, that stable points, some of the stable points here are mapped onto out of the unit circle, which means unstable. Okay, right. What about backward difference method, right? So the backward difference equation is this: IB, B for backward, IBK minus 1, the previous error integral, times EK times T. So graphically, it's like this. You are over here, K minus 1, this is K. So you take EK, the error now, and multiply with the time and add that to the integration. And in this particular case, you are adding little more to the integrator, versus a little less the previous case. It doesn't mean that you are always adding something new, right? Sometimes you can go the other way around depending on the curvature. But anyway, it's also not good, right? It's not very accurate. Anyway, let's go ahead and find out the relationship between Z and S. So in the Z domain, this becomes IBZ. This is Z to the minus 1. IBZ. This is EZT. Okay, there's no Z to the minus 1 over here because this is the time sample at K. So once you simplify this one, eventually you get down to 1 over S. The integration is approximately modeled by ZT over Z minus 1, right, over here. Error goes into this block, and what comes out of that is the error integral. So therefore, the block has to be an integrator, right? In time domain, it is 1 over S, and in Z domain, approximately ZT over Z minus 1. Now, after little mathematical manipulations, you can actually get Z as the subject of the equation. It will be 1 over 1 minus Ts. This is the mapping. Now, as we did earlier, you can substitute t equals 0, this point, and the answer is 1, z equals 1. So same as earlier, this point is mapped onto this point. 0 is mapped onto 1. What about infinity? If you substitute s equals minus infinity, this whole thing is 0. You map it onto this point. Right? 0, infinity, 1 to 0, which means the entire negative half plane is mapped onto another area somewhat similar to a circle. It's not exactly a circle, something like that, well within the unit circle. So therefore, stability wise, there's no problem. But you will see there's a huge area that we are not using. So therefore, even though this is stable mapping, this is not very accurate. There's no stability problem, but there's a little accuracy problem. Okay. Any questions, please? Is everything clear to everybody? Shamira, is everything clear to
Yes,
you? Dhananjay?
yes, it's clear, sir.
All right. Vihangi?
Yes, sir.
Right. Chaturanga? All right. Now, there's another method. We call it Tustin approximation, a British engineer actually figured that out. The previous ones, the Euler integration, right, has these problems. He came up with this bilinear approximation. We call it Tustin approximation. And he said this, when you do the numerical integration, you take the previous sample and the present sample and get a trapezium, right? This is a trapezoidal shape as the additional quanta that you add to the previous integral to update the integral, right? So the equation is the previous integral plus ek minus 1, this error, plus ek, the present error, divided by 2, multiplied by time t. Fine. And visually also, you will see it is much more accurate than the forward difference or backward difference methods. Let's see the mathematical proof of it. Again, as we did previously, let's convert this from time to z, the z transform, and this will be itz. So t stands for Tustin. This is z to the minus 1 iz, itz, and this is t by 2 z minus 1 ez plus ez. Then you bring this one to the left hand side and multiply every term with z. So then this will be z minus 1 times iz, itz actually. On the right hand side, t by 2, this is z plus 1 ez. And once you simplify, you will see it like this. Integrator is approximated by z plus 1 over z minus 1 times t over 2. This is yet another approximation. And once you invert the two sides, you get the reciprocal s 2 over t z minus 1 over z plus 1. Or if you want to get z as the subject, it will be 2 plus ts over 2 minus ts. So with that, now you can map from S to Z and see what you get. So it's a much better mapping. You can see it over here. As S goes to 0, Z goes to 1. This point is mapped on to here. Z goes to infinity, S goes to infinity, Z goes to minus 1. Perfect, right? And if you put any other thing, S goes to minus 2 over t, something like that. Z goes to 0. So over here. So you are mapping entire negative S-plane onto the unit circle. So therefore, this is not only stable, but it's much more accurate than forward difference or backward difference methods. Now, therefore, because of this reason, this is the most commonly used discrete integration technique in digital controls, right? So it doesn't have the problems that the forward and backward difference methods suffer, right? Right. Now, if you so I think now maybe you can deal with the aliasing problem by filtering or sampler selection, and also whenever you want to calculate differentiation or integration, approximate versions of those in this digital control systems, you can use Tustin and other techniques, right? You might think, yeah, you can manage the situation with all of these. You are right that this is exactly what control system engineers and designers do, right, on daily basis. But when you dig deeper and deeper and deeper, you will see a lot of problems, basically for research, right? For engineering practice, you don't need to go that far. Now what we are going to do is we are going to look at the frequency distortion digital approximations, right? We are going to use Tustin, for example. Tustin. So up to now, right, Tustin is your best discrete approximation, but it's not perfect. It's not perfect. So we are going to see what are the imperfections in Tustin. So we recall the relationship between Z and S in Z transformation. Z equals e to the st. Okay, and S equals j omega, the complex frequency. In Tustin, what's going to happen? We will put it like that: Z equals e to the j omega t. S in the place of S, we call it j capital omega t. So why I use capital omega t? Because I don't know whether Tustin is mapping the frequencies without any distortion. Let's say if you use 10 hertz signal, right, into the Tustin to calculate the error integral, I don't know whether same frequency is going there or is there any distortion. Now, in the sampler, maybe not a lot of people thought that it was actually doing this aliasing stuff, right? Creating something totally out of non-existence, right, into the system. So similarly, uh, let's put a different symbol there for the frequency, that is capital omega. After going through this Tustin approximation, right? And if there's no distortion, we will see capital omega equals simple omega, right? Simple omega is the actual frequency that goes into the process. So we know in the Tustin approximation, right, S is equal to 2 times Z minus 1 over Z plus 2, 2 over T in front, right? That is this equation, this one, right? This is the relationship between S and Z, right? Now S is the continuous signal. And now if you just think of a monotonic frequency, just a single frequency, right? We call it j omega. So j omega is the signal that goes into the Tustin, right? So here we write it like e to the j capital omega t, right? Because capital omega t is what the Tustin sees. Tustin may not see omega, but it will see as capital omega. We don't know, right? We'll put a number, symbol different to simple omega and see what's going to happen. And over e to the j capital omega t plus 1. And we multiply numerator and denominator both here with e to the minus j omega t by 2 this time, t by 2, okay? So then what will happen is that because of this negative, right, it will be just plus j omega t by 2 minus, because this one here, it will be e to the j capital omega t by 2, like that in the numerator, and the denominator will change like that. So now you get 4 terms, right? 2 in the numerator, 2 in the denominator with very similar exponents, right? J omega t by 2, sometimes minus, sometimes plus. And if you look at the numerator here, this is actually 2j sine omega t by 2. And in the denominator, this is 2 cos omega t by 2, right? Sine and cos. So then 2 cancel out, then this becomes tan omega t by 2, right? And eventually we have a relationship between capital omega and simple omega, right? Either this way or that. If you want to calculate capital omega, simple omega from capital omega, this equation, or capital omega from simple omega, this equation. right? So what we predominantly use is this equation, right? Because we know what goes into the integrator, that is omega, we know that, and we want to calculate this one, right? You will see that this is highly non-linear because it's tan inverse, right? Mapping between omega, simple omega and capital omega. So your frequencies will not be the same even within the Tustin approximation. There is some sort of warping in the frequency domain, right? Now it's time to draw the mapping curve between omegas, right? Simple omega and capital omega. And horizontal axis is the continuous time signal that is being subjected to numerical integration using Tustin, and vertical axis is what the Tustin sees, these frequencies, right? It's capital omega. You will see it's not quite the same, right? You go like that, and then you have this symptotic uh, reaching at pi over t. This is the pi over t is the sampling interval. So this Tustin is operating at a certain frequency, right? So you get half of that frequency, and that is the limit. All of the frequencies, right? They are mapped onto like that. So you saw that in a previous one over here. All of the frequencies, whatever it is, right, are all mapped onto unit circle. All right. It doesn't allow anything to go out of that. Everything within the unit circle, which means stable, right? Stable means you don't have any frequencies, right, that can potentially destabilize the system. So it looks like this. I think it's good. There's nothing wrong. This warping is not a big problem. In fact, it's a plus point here, right? Now, we have two ways to go. Whether you want to have a straight linear approximation, mapping between omega and simple omega and capital omega, or deal with what you have here, with all the benefits therein, stability and so on. And if you come closer to the origin, somewhere over here, you will see this is 45 degrees. There's some linear region here. This is the perfect mapping between omega and capital omega, right? All of these low frequencies, right, that goes into the numerical integrator, Tustin. Tustin also accept it as it is without any warping, as long as they are very small in this area. So then you can say this, I want to have a very accurate numerical integrator. I will use Tustin for that. And also I want to have the system to have stability. Again, Tustin is good. And I also don't want to see frequency warping, right? When it comes to that point, third point, I would say I will stick into the frequencies in this area, right? Around the origin. So therefore, the graph between simple omega and capital omega is a linear portion. I don't actually see anything beyond that. This curvature, I don't see. I don't have that omega in my signal. My signal is limited to the small part, so therefore mapping is linear. I don't have to worry about frequency warping or signal distortion, right? So this is how we do. If you look at the practicing control systems out there in industry, sometimes they even don't know about this frequency warping and all that, because system is designed by not by the practicing engineers, but some other set of people, designers, and they take care of all these things and make sure that your frequency bandwidth is limited to that portion. So therefore, there's no frequency distortion. All right. So This is not a problem of the practicing engineers, but this is a problem of the designer, control system designers, right? But for you guys as grad students, you need to know a bit of everything, right? How it happens, and when it comes to practicing, what is it? When it comes to designs, what they are, right? Any questions, please? Is everything clear? Or any questions?
So here, what's the graph would say is if we are considering only for the until the Nyquist frequency, we don't want to consider about the rest of the graph. That's but
Yeah, partly yes, but I don't want you to go even to Nyquist level, right? Maybe far below that, right? Maybe a quarter Nyquist limit, right? Is a good choice so that it will be more linear, right? In fact, this is not a linear curve at any point. It is entirely a non-linear curve, but it is more and more linear when you go to closer to zero. So therefore, if you stick to your frequencies, right, maybe 1/3 of the Nyquist or 1/4 of the Nyquist, yeah, smaller the better. Smaller the better. Now, how can you go for 1/4 of Nyquist or 1/3 of Nyquist? Is by selecting the sampler, right? You select a sampler, sufficiently fast sampler, so then your Nyquist is high, your quarter Nyquist is also high. Understand? So the determination of the sampler, the sampling frequency, is very, very critical, therefore. And it can solve a lot of problems in your digital control system. So if I can name one single piece in the discrete control system which is most important, I would pick up the sampler, definitely. Any other questions, please? Let's read through some of these notes here. Note 1, use trust-in approximation in discrete time integration to avoid stability issues, right? While maintaining better accuracy, less distortion. That's fine. Then the second sentence goes like, all the techniques in discrete time integration have distortions at high frequencies. You can see it over here, even trust-in, there are warping, right? Especially around and above Nyquist frequency, this area. Therefore, it is recommended to use a substantially higher sampling frequency. So, substantially means generally maybe 4 or 5 times, right? Not too high, because if you consider very high speed sampling, again, you are talking about high bandwidth, high speed electronics, expensive. It's not needed. Depending on the accuracy there, up to what level you can tolerate the errors and all, you have to make that decision. So let's work this out. I want everybody to turn on your videos now again. This little exercise, we're going to do it together. Why don't you turn on your videos for a moment, because I want to see you guys. Take a piece of paper and start working. Right. So what have we got here? Calculate frequency distortion of 10 hertz, 20 hertz, and 50 hertz when sampling takes place at 120 hertz and 250 hertz and 1 kilohertz. So what is it? So there are three signals, right? 10 hertz, 20 hertz, and 50 hertz, right? So there are three signals coming in, right, in your feedback path. And then you have tasked in to do the integration, numerical integration. Maybe you are going to use a discrete PID, whatever it is, right? We don't know those details. And there's a sampler. Sampling takes place at 120 hertz. So there's a sampler already there. And the trust-in integration is implemented on the 120 hertz sampler. And there are frequencies coming in, right, to the discrete integration. So this is the situation. You can see it over here, right? This is the incoming frequencies, right? And this is the trust-in. There is this sampler over here. So you are supposed to calculate the frequency distortions, right? Which means, what is it for 10 hertz in trust-in? What is it for 20 hertz in trust-in? And what is it for 50 hertz in trust-in? Right? Does trust-in see 10 hertz as 10 hertz, or 20 hertz as 20 hertz, or 50 hertz as 50 hertz? That is the question. The answer is very simple. It's just one equation like this or like this. I think we better go for this one, right? Because all the frequencies are given in cyclic frequency terms, hertz. So we better use the second equation. Fo means the frequency that is seen by trust-in is Fs over pi tan inverse pi Fi over Fs. So this is basically conversion from this equation, right? I think you are pretty okay with that. Converting from omega to radians per second to cycles per second. Please calculate it quickly and tell me your answers. Unmute your mics and tell me your answers. What is it for 10 hertz? Has anybody got the answers? You can unmute and tell it to us, or you can write it in the chat. For FS 120, 9.7. So 10 hertz get down to 9.7. This is from somebody 228686p, right? I don't know the name. 10 hertz is seen as 9.7, close enough, and 20 is seen as 18.4, and the other one is 30 hertz is seen as 35 hertz. No, 50. 50 hertz is seen as 35 hertz. So that is one answer. Right? This is my answers. For 10 hertz, under 120 hertz sampling. Okay, this is important. Remember, this all depends on your sampling frequency. Now, if it is 120, it looks like this. 9.7 for 10 hertz. So close enough. For 20 is 18. But for 50 hertz, it's 35. This is a problem, right? You don't actually get the 50 hertz. It looks like 35 hertz. So this is not because of aliasing, right? Because if you look at aliasing, there's no aliasing for 50 hertz, right? Sampler is 120, right? Sampler is 120 hertz. This is 50 hertz. So well below half of the sampling frequency. So there's no aliasing here, but there's some sort of distortion, frequency warping, because of the Tustin approximation, which is by far the best numerical integrator. Yet you see 50 hertz is seen as 35 hertz. Okay. So this is the reality of dealing with signals in the discrete time. So that is why it says Nyquist theorem is not the rule to be followed, right? It is the ultimatum. So therefore, half of the Nyquist doesn't mean anything in reality, right? So if you are a control system designer and you have the proof here, 50 hertz has a lot of problems. 20, I think 20 is okay. 20 hertz is seen as 18 hertz, close enough. So therefore, our rule of thumb when it comes to sampling is not the Nyquist. It should be what? Say, according to at least this example, right? It's 40 hertz versus 120 hertz. So in other words, you have to go the other way around. 120 hertz, right, gives you a serious problem with 50 hertz, right? So if you want to get 50 hertz back on track, just like 20 hertz here, right, you need to improve your sampling rate further up few times. 120 is not enough, maybe 250 or even more, right? So generally speaking, when you select a sampler for a plant, you go for, let's say, you know your bandwidth and go for maybe 5-6 times higher of the bandwidth. So if the bandwidth is 10 hertz, right, your Nyquist says 20 hertz, but you go for 80 hertz, maybe, right? Okay. So what do we have here? Please do this later. I have the answers on screen. 250. If you increase 250 to 250 hertz, right, sampler. Earlier it was 120, now 250. The numbers will change like this. 10 hertz is now seen as 9.95, very close. And 20 hertz is seen as 19.59. And 50 hertz is seen 44.64. I think marginally okay. 50 hertz is seen as 44, right? But you have to increase sampling from 120 to 250. What about 1000 hertz? If you have a 1000 hertz sampler, 10 hertz is seen as 10 hertz. There's no error at all there. It's perfect linear mapping, 10 hertz. What about 20 hertz? 19.97, pretty close, very close, right? And 50 hertz is mapped as 49.59. And remember, this is asymptotic approach. So therefore, you don't get exactly what you want except very low frequencies. So getting very close is enough, right? Don't try to have a perfect match because it will be extremely difficult and very, very high speed sampling that is required. All right, so we have learned a lot of things on that. Simple satisfaction of Nyquist theorem is not good enough. If you have to look at the signal warping due to numerical integrations and any other numerical discrete signal processing. And as a result of that, you need to increase your sampling frequency way beyond the Nyquist limit. Okay. Then the last discussion on this line is pre-warping. Pre-warping. So I will get the start point right over here on what you see on screen. You will see there's some distortion, right, in these frequencies. In some frequencies there's no distortion, right? It naturally happen in the lower frequencies. You don't get a distortion, and higher frequencies you get distortion. Now let's say we have a bandwidth frequency, right? Maybe 20 hertz, right? 20 hertz. So now the critical frequency is 20 hertz, not 10 or 50. So which means we can accommodate some errors in 10 hertz and 50 hertz, but it's good not to accommodate any error at the bandwidth frequency, that is 20 hertz. Okay. So if I go back to the first case here, I want to change this to what? I want to change this to 20. I want to change this to 20 by adjusting some way, and I can actually accommodate more error, little more error here and here. I don't really worry about 10 hertz or 50 hertz, right? But I really do care about the distortions at 20 hertz. So is there any way for me to improve the accuracy, frequency warping, or reduce frequency warping at 20 hertz at the expense of more errors at other frequencies? So this is what is called pre-warping. So qualitatively speaking, it's like this. You have the warping process in the tasting. If you send the original signals, they undergo this warping and you get this result. 20 hertz will be 18. Now what we do is we put another block in front of that, which is called pre-warping. It will warp the frequencies before Tustin takes over, and the warp signal goes to Tustin, and Tustin will introduce another warping, right? So eventually there won't be any change in the frequency at 20 hertz. So you get the same 20 hertz, right, after Tustin. So what you need is another block in front, which we call pre-warping. It's like this. So you ask for something, you get something else. You know the equation, and you ask something that you don't want, and you will get what you want. It's something like that, right? Let's say you ask a salary hike, right? 10%, and you always get half of that, 5%. So why don't you ask twice as much you want? knowing that you get half of that, which is exactly what you want. Something like that, right? So we call it pre-warping. So let's look at the mathematics of pre-warping. And over here, I have trusting again for you to look at it clearly. This is trusting approximation in time domain. And this is the frequency or Z domain. And this is trusting based approximation S and Z. Okay, right. Um, so now what I'm writing here is an equation coming from Tustin, but slightly different. If you look at the Tustin approximation, it is ITK plus 1 plus addition of the two errors divided by 2 times time, right? This one. So there you can see I have T over 2, right? This T over 2, but I write it like this over here. In place of T over 2, I write 1 over alpha. I bring in something out of nowhere, right? I arbitrarily change the equation using this alpha, right? We do these kind of things quite commonly in mathematics. Finally, we are going to calculate the value for alpha to, to achieve what we want to achieve, right? So this is not the original Tustin. This is the pre-warped Tustin. So therefore, I write it like IT sub P, right? Superscript P to indicate that this is not the original Tustin. This is the pre-warping. Okay. So we don't have T over 2 over here, but 1 over alpha. So T over 2 is 1 over alpha. So what I'm trying to do is this. If 1 over alpha is less than T over 2, I squeeze this area. This is the original area. I squeeze the area. I don't take the full accurate amount. I reduce it a little bit. If I have 1 over alpha greater than T over 2, I get more than what it is. Right? Both are not correct. But pre-warping is anyway not correct. It is a distortion that you introduce in order to cancel another distortion at a later stage. Okay? So if we proceed with this equation, right, this is what we get for the numerical integration. In place of T over 2, it is 1 over alpha. Rest remains the same. So therefore, 1 over S integrator would be 1 over alpha like this, and S and Z is now related with this equation. Okay. What we don't have here is sampling interval. Instead, we have another quantity called alpha. Now, if we select alpha so that in frequency mapping, that is omega PO equals simple omega, that is frequency in Tustin, and this is the actual frequency omega, right? They should be equal for no distortion, right? With the pre-warping, if you want to have no distortion or zero distortion at any frequency, you can write it like that. Okay. Okay. So continuous time frequency and the discrete time frequency with pre-warping are equal. So you can set this clamping of the equation at any frequency, but only one frequency. Okay. You can't do this for different frequencies. Only one frequency you can do this clamping. Rest of the frequencies, they have different distortions as a result of this. Okay. So our frequency mapping is now this: omega equals alpha tan omega pt over 2, and if I want to do this like omega 0 is equal to alpha tan omega 0 t over 2 when there's no distortion, because simple omega, capital omega, they are both equal to some omega 0. Clear? So we are clamping the equation for zero distortion at some frequency omega 0. So at omega 0, right, omega simple and omega capital with pre-warping are equal, and you get the alpha calculated this way, right? So from this equation, you can calculate alpha. Let's call it alpha subscript omega 0. This is the alpha for zero distortion at omega 0 frequency, right? Is that particular frequency, whatever it is, omega 0 over tan of omega 0 t over 2. Clear? Or in particular frequency, cyclic frequency terms, not omega, radians per second terms, the same equation will look like this: 2 pi f0 over tan pi f0 over fs. Only difference is you substitute for omega using f. Omega equals 2 pi f, just that. Okay. Now you can go back to the drawing board again and pick up sampling frequency and whatever frequency you want, zero distortion, and calculate alpha for that. And then after that, you use not the original Tustin, but this equation, pre-warped Tustin. So your numerical integration will differ. It's not the standard Tustin, but pre-warped Tustin. Okay, you can go ahead and do the integration like that, and you will see no distortion at omega 0 or f0. Do you have any pre-warping exercises? Now it comes in assignment. So I will upload the assignment today. I have 2 assignments. I will upload and give you enough time to work on. The assignment 2 is like this: draw frequency distortion graph of Tustin approximation for sampling at 250 Hertz. Draw frequency distortion of Tustin approximation for sampling at 250 Hertz and pre-warped at 20 Hertz. There you are. I want you to pre-warp this at 20 Hertz. So omega 0 will be 20 Hertz, and you calculate alpha 20 Hertz accordingly. Compare and comment on the two frequency distortion graphs. Calculate alpha for pre-warping at 50 Hertz when sampling takes place at 250 Hertz. Okay, so these are all doable. 2 simple equations. That is all what you need. And do that assignment and submit to the module. Yeah, that's about it. Any questions, please? All right. So if there are no questions, let's wind up the session today.